All right, so for this video, we're moving on to 2.4, which is special pairs of angles. If you'd like to follow along in your textbook, this starts on page 50. Okay, first thing we're going to do is define complementary angles. If two angles are complementary, then their measures have a sum of 90 degrees, and each angle is the complement of the other. So I might say angle 1 is the complement of angle 2, which means their sum is 90. Now this can look like almost anything that adds to be 90. The angles don't necessarily have to be next to each other. Sometimes they are, sometimes there aren't. So just quickly, for example, maybe you have a situation with a right angle, and that angle is being split by a ray, and maybe one angle is 40 degrees and the other is 50 degrees. This is an example of complementary angles. But the angles also do not have to be adjacent to each other. Maybe you have angle A that is 45 degrees, and maybe you have angle B over here that's also 45 degrees. Since their sum would also be 90, they're still complements even though they're not adjacent. Supplementary angles. If two angles are supplementary, then their measures have a sum of 180 degrees, and we would say each angle is the supplement of the other. So angle 1 is the supplement of angle 2. These can also look like a few different things. You don't have to have them next to each other. So your book shows angle A and angle B, where angle A is a 50-degree angle, and then you have angle B that is a 130-degree angle. Their sum is 180, so those would be supplementary. You could also have a linear pair. We defined linear pair in 1.5, in the 1.5 notes. That's when you have a pair of angles where their non-common sides form opposite rays. So it would look something like this, okay? So you have your opposite rays at the bottom here. So these two angles would also be supplementary to each other because we have a straight angle, right, with opposite rays down at the bottom. So one angle would be x and the other would be 180 minus x. So again, maybe 50 and 130 or something like that, but that's another way that could look. Vertical angles. If two angles are vertical, then the sides of one angle are opposite rays to the sides of the other angle. So what that looks like is kind of just two intersecting lines. So when you look for vertical angles, you want to look for two intersecting lines, maybe something like this. Okay. Now the question is, which one of those are vertical? Well, what I'm going to do here is label this 1, 2, 3, and 4. Now, angles 1 and 2 here are actually a linear pair. 2 and 3 are actually a linear pair. 3 and 4 are a linear pair, and 1 and 4 are a linear pair, right? Because you have your opposite rays. Vertical angles are non-adjacent. So the ones that are non-adjacent here would be like angle 1 with angle 3. So those would be vertical angles because they're formed by those two intersecting lines. So in this example, we would say angle 1 and angle 3 are an example of vertical angles. And then also the other way, 4 and 2 would also be an example of vertical angles. Okay, so you should look for your intersecting lines. Our first theorem for this actually has to do with vertical angles. It's the vertical angle theorem, and that just says vertical angles are congruent. If you take a look at the X shape we drew here, right, if you folded that in half, 1 on top of 3, they would line up perfectly. These are always congruent. So what we're going to do in this proof is we're actually going to prove our vertical angle theorem. So we are going to draw our own diagram. You can reference the proof on page 51 for this. So I'm going to draw our diagram here. It was very similar to what I drew above. Draw your two intersecting lines. Okay. And we have angle 1, angle 2, and angle 3. We are given that angles 1 and 2 are vertical angles. We want to prove now that they are congruent. So let's go ahead and fill in some of our information here. We have our given that angle 1 and angle 2 are vertical angles. I know that in the book, it does not list that in the proof, but I always put the given. And then our proof, our last step here is going to be that angle 1 is congruent to angle 2. Now you're going to notice that I do a few things with this slightly different than your textbook. Okay. So do what I do, not necessarily what the textbook does. Because the textbook, in my opinion, does a few little things that are extra that I just don't think are necessary. Like I don't think it's necessary to use the reflexive property every time you want to subtract. But I do think it's necessary to show the difference between congruent and equal. So you'll kind of see what I mean with that. We actually did that up above in 1.3 as well, when we used our definition of congruent, either segments or angles, I can't remember. So we have some vertical angles here. We know that. And if you look at your picture, this is a perfect example of sometimes your picture is going to give you necessary information. And if you look at your picture here, we actually have some linear pairs, right? We have that angle 1 and angle 3 right here. That is a linear pair. We have our opposite rays, right? So what we know about these, if we think about our angle addition postulate, angle 1 and 3 are going to have to add up to be 180 degrees because we have our straight angle here. And then we have the same thing going on with angle 3 and angle 2. We have our straight angle, so those are going to also add up to be 180 degrees. Then what's going to happen is they both will share angle 3. We'll be able to then subtract that out and get that the two angles are equal and then congruent to each other. So first, let's do our angle addition postulate, and we're going to add up our parts here. Because we know that they're vertical, but we are going to need to somehow figure out how to set them congruent to each other. So we need some type of equation or congruency statement. So we're going to say that the measure of angle 1 plus the measure of angle 3 equals 180. And in the same line, I'm going to do the same thing with 2 and 3. The measure of angle 2 plus the measure of angle 3 equals 180. I'm combining these into one line because I'm using the angle addition postulate for both. Okay. So that's our angle addition postulate. And then with this, we can now see that both sets of angles are equal to 180. Right? If they're both equal to 180, we can go ahead and say they are congruent, or I'm sorry, equal to each other. So we're going to say that the measure of angle 1 plus the measure of angle 3 equals the measure of angle 2 plus the measure of angle 3. Now your book calls this substitution. I would 100% accept substitution because you're replacing one with the other. However, you can also look at this and think transitive property because they both equal 180 degrees. And the transitive property can be used with both equality and congruence. So I would also accept the transitive property here. So whichever is more logical to you is the route I would take here. So substitution or transitive. Again, they're both clearly equal to 180, so that could also be the transitive property. Now, we have the measure of angle 3 on either side. We don't want that there anymore. We want to just end up with angle 1 and angle 2. So if I'm adding that to either side, I can now subtract it out and be left with the measure of angle 1 equals the measure of angle 2. I subtracted from both sides, so that is the subtraction property. Now, this is an example of where your book and I are going to differ in opinion a bit. They actually combine my last two steps into one. They say that the measure of angle 1 equals the measure of angle 2, or angle 1 is congruent to angle 2. I disagree with that. I think that that needs to be two steps because equations and congruency statements are two different things. They're different labeling. They require different symbols and things like that. So when we say something is equal, we can say it is congruent as well, but you need to actually state it. It does have a justification. It is a definition that we've learned. So when I'm switching from saying measurements are equal to congruent, right? Equal measurements means congruent angles. That's the definition of congruent angles, right? If angles are congruent, then their measures are equal. So that is the definition of congruent angles. All right, and then we are going to just look at some examples here. So number 1 here, given angle 2 is congruent to angle 3. So that's referring to this diagram here. So angle 2 is congruent to angle 3. What can you deduce? So you got to kind of look at this picture and think of our new theorems and our new definitions. So if I know that those two angles are congruent, what else do I know about this picture? Well, if you take a look, I have lots of little X shapes here. I have several pairs of vertical angles. So I know that angle 2 is going to be congruent to angle 1. I also know that angle 3 is going to be congruent to angle 4. Therefore, I can conclude that angle 4 and angle 1 will also be congruent. So what can I deduce? I can deduce that angle 1 is going to be congruent to angle 4. How did I get there? Well, instead of writing a formal proof, we're going to write kind of an explanation, because proofs are basically just well-structured explanations. So what we're going to say here, and there's several ways to state this, but we have vertical angles, right? So we're going to say that angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4 because, and now with this part, you can either say because of the vertical angle theorem or because vertical angles are congruent. Again, whichever you prefer. So because vertical angles are congruent. So then, if those angles are congruent, and from our given information, we know that angle 2 is also congruent to angle 3. Well, if those two angles are congruent, we can then conclude angle 1 is congruent to angle 4 by the transitive property. Because remember, the transitive property works both for equality and congruence. And if two things are congruent to the same thing, they're congruent to each other. And so angle 2 and angle 3 would have to have the same measure here if they're congruent. So we can conclude that 1 is also congruent to 4. So then we're going to say angle 1 is congruent to angle 4 by the transitive property. then number 2, in the diagram, the measure of angle AXB equals 90 degrees. So AXB is 90 degrees, and they were nice enough to put a little right angle in there, right angle symbol in there for us. So we want to name 2 congruent supplementary angles. So that means 2 angles that are going to add up to be 180 and be congruent to each other. Well, the only way that can happen is with 2 90-degree angles. So that's going to have to be our 90-degree angle that we're given, and then the one on the other side, since we have a straight angle at the bottom, or linear pairs. So we're going to say angle ABX and angle BXD, or DXB if you prefer. 2 supplementary angles that are not congruent. So again, they're still going to add up to be 180, but this time they're not congruent. Again, if you're looking for things that are supplementary, look for straight lines, straight angles, right here, AXD is a straight angle. So I would say angle AXC and angle CXD. Those are going to add up to be 180, but they are definitely not congruent. One's obtuse and one's acute. So we're going to say angle AXC and angle CXD. 2 complementary angles, so 2 angles that sum is 90. Well, if we had a right angle here on the left, we're also going to have one on the right, since we have a straight angle on the bottom here. And that's being split up into 2 angles, angle BXC and angle CXD. So angle BXD and angle CXD. And then name a straight angle, that's our angle along the bottom there. We're going to call that angle AXD. Okay. Let me know if you guys have any questions, especially about the proofs and the theorems.